I minus equal for omega I and all those things you have when the solution has periodicity for the homogeneous system. When the solution has a periodicity for the homogeneous system, how it goes, and then so periodic solution for the this non-homogeneous system and the periodic solution for the non-homogeneous system. And we have found that periodic solution for the non-homogeneous system, if it exists, solution will not be periodic for that particular case, for the homogeneous system. Okay. And also, the last problem was very interesting, what I asked you to do at home. Did you able to finish it? No, so no time. Okay, so last problem we look at, there are two kinds of periodicities, 2 pi and pi. And if you see 2 pi, there is some problem. Because, see, I minus e to the power omega A in that matrix can be singular, can be non-singular. If it is singular, then the periodic solution will exist for the homogeneous system, and it will be periodic for the non-homogeneous system. Right? So try to verify the last part of the problem for the periods 2 pi and pi, and you will see the interesting results there. So that's why I wanted to do that. Okay, 2 pi and pi. Okay, so how many assignments have given so far? Problems at 5, right? So CR can come here. So I will be giving now problems at 6 for the functional space. It has 2 pages, both back to back. You can go. Give it to me on Monday. So we are going to start now. So far we are talking about Ax equals to B. So far we are talking about Ax equals to B. So what actually we have done? We have done how to. We have learned also about what is vector space. We have learned the properties of the vector space, like matrix, norms, and then non-linear space, and the inner product space. Right? First we talked about the vector space. First we talked about numeric, then vector space, then the metric, non-linear space, and then angle between 2 vectors. All those things actually was discussed. Then we want to talk about the basis vectors. So what we did, I will just summarize properties of vector space. Properties of vector space. Then we have numeric field, metric, non-linear space, and we have inner product space. Okay. Then we talked about the basis. We talked about the basis set. We talked about the basis set. The basis set, what we did, we generated the basis vectors and then talked about the solution Ax equals to B and X represented in terms of basis, and we concluded eigenvector as best basis, eigenvector as best basis, that we also concluded, right? Basis vectors, middle bench. Yogesh should be sleeping. You are sleeping. I asked him, I saw, are you sleeping or not? He will say no. I am not talking, I am asking him. You are not sleeping. So then I am blind. You are proving that, right? Are you sleeping or not? I am asking. Now you are not sleeping, but 1 minute back you are sleeping. Problem, right? Probably, okay. You know how to do it, make good answer. That's what I am telling you in this class I can get some of the future ministers. And you will be one of the, you have a very high chance to become a minister. And I wish you all the best to do that. And at least help us, to become minister. Ministers do that. In the cabinet meeting, if you go there, some minister will shout. They will not do anything. Some minister will sleep. And they are the most productive ministers. Whatever is happening in the country, for the ministers who are sleeping in the cabinet. They because of their confidence, they will not be able to improve it. So I really appreciate you doing it, and that will be good for our country. So eigenvectors are the best basis sets. Okay? And we had all sorts of things. From there, we actually applied adjoint, got the properties. Then what we did, we applied this system for the differential operator, which is having dx dt equals to a, and applied all the properties here, solve the system. These are the things we have learned so far. Okay, I think I have summarized whatever we have learned. Now, and of course, we also said this is the linear operator. We said it's a linear operator. The thing is that this is the vector space. This is vector space. Okay. So then one can have functional space. Then one can have functional space, and the functional space is, of course, we have a u equals to a. A is the differential operator. Okay. So typically you can say d2u dx square equals to a, and this both the systems are identical. Okay. Here u is function and x is the vector. Where b is the vector, f is the function. The question is, can you convert, if I give this one, can you convert to this one? It can be done, but from here, it cannot be done. It is an irreversible process, not thermodynamically reversible, mathematically reversible process. How to get from here to here? How to get? You know the answer.
U by dx is equal to t or something. dt by dx.
What du by dx t? It is a steady state process. How can you say t? Where is t coming?
Any variable.
Okay, I'm saying x. No other variable will be there. Du by dx equals to z. Then z by dx equals some other variable. Huh? Dangerous. Let's take something dangerous kind of items. Have you done finite difference method? What we do in finite difference method? This is the overall domain 0 to 1. This equation is validated, so you can have boundary conditions. Say u x equals to 0 equals to 1, du dx at x equals to 1 equals to 0. You can solve the system. This is my complete problem. I want to solve between 0 to 1. But in finite difference method, what we do, we discretize the domain. I will discuss later. Finite difference method. We discretize the domain and we solve all these discrete points. What we do, for example, if it's a ith point, we write du dx equals to ui plus 1 minus ui by delta x. Forward difference method. This I plus 1, this is I. Forward difference method. I am just being very simple. And similarly, you can write d2 by a square equals to ui plus 1 minus 2ui by implies ui minus 1. Am I correct? This kind of things are discussed. This is the way we actually write. If you don't know, let's do that. So this is at x equals to I. At x equals to I point, you can write this. Now you can see this entire differential operator. Remember that du say these are the ratio. This is the ratio. When I put limit delta x tends to 0, everything has become calculus. In calculus, du by dx, it is not d by division. It is called as ddx of u. ddx means limit delta x tending to 0, delta by delta x. But this is the algebraic expression. Now the situation is, if I have u that is linear, then we can say that doesn't matter delta x 0, because this varying linear we can write this is delta u, this is delta x, and we can replace du dx by delta u by delta x. This is the philosophy of the finite difference method. And delta u is 2 points means ui plus 1 minus ui by delta x. That's why I know. This is the philosophy. If it is not varying linearly, this approximation will not be valid, and your numerical result will be wrong result. So this is the philosophy. So with that philosophy, dq by dx square can be written in terms of algebraic expression. Right? Can be written in terms of algebraic expression. So dq by dx square x equal ui plus 1 minus 2i plus ui minus 1 by 2 delta x. And then in that case, what actually happen? This will get so many sets. It will be valid from say I equals to 2 to I equals to n minus 1, because I equals to 1 boundary condition is there, I equals to n boundary condition. I can apply I for I equals to 2 to I equals to n minus 1. If I put I equals to 2, what will happen? u3 minus 2u2 plus 2u1 equals to something. Then you get I equals to 3, u4 minus 2u3 plus 2u2. Like that you get set of linear algebraic equations. The unknowns will be what? u1, u2, u1. These are the unknowns. So you can see you are getting variables evaluated here, and the entire system is now converted a system called AU equals to B, where U size is n. So that's why the vector space is a finite dimensional system. We have seen that. Now when you talk a particular problem, a vector space problem, you are evaluating here, 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 here. Like the 10 points are there. Like the 10 points are there. So definitely by analyzing this process, one can say that vector space is a finite dimensional space. But if you solve this, you can get anywhere the values, because you get in terms of x. For example, if du when dx is f is constant, what will you get? You will get what? Fx plus c, something like that. Afx plus b ddx of this fx square by 2 plus bx plus c, something like that. Fx square by 2 plus bx plus c. And b and c can be evaluated this. That means u is a function of x. Any value of x, you get the answer u. But this method, you will be getting solution only in these points. So that means it has got solutions. When you talk, it has got solution between infinity, any point from here. But this will give at these discrete points. So the same problem can be treated as finite dimensional vector space as well as infinite dimensional functional space. So that means what we have learned from this vector space is finite dimensional, but functional space is infinite dimensional. Okay? So vector space is finite dimensional and functional space is infinite dimensional. Okay? Any question? Any question? Any doubts? I will give another example. So differential equation. So we can see that this entire problem has been converted to x equals to b by this different. But if I give any kind of matrix, it will be difficult for you to go to the functional space. It is difficult. It is difficult because functional space requires the boundary condition. Once you discretize the boundary condition, the concept is lost. Okay? You are actually saying that my points, I have these points and these points are connected. That's why sometimes this is called as connectivity matrix. They are connected. The information of connection is there. Boundary is what is happening here and here. Without that, we cannot solve the system. Okay? So, the vector space, when you represent, we are losing a lot of information. In between what is happening, one information you are losing, and also at the end point what is happening. But definitely this entire problem can be expressed as a vector space problem. So vector space is basically the finite dimensional problem. We have a lot of approximation. Functional space advantage is we have infinite dimensional problem. At any point we are getting the solution. That's why we always prefer to have analytical solution over numerical. That's why I have been teaching numerical very small portion. Only last 7 or 8 lectures. Because analytical should be given fast. If you are not getting analytical, then go to the vector space. So when you do numerical, essentially you are mostly working on the vector space. That's why entire numerical techniques. If you talk about numerical analysis or numerical course, mostly numerical analysis deals with vector space. Okay? But our analytical solutions will have vector space as well as the functional space. Another way to look at the functional space, as I said, the concept of mirror will be still valid. The concept of mirror. The concept of mirror. Concept of mirror will be still valid here. We say Ax equals to B. What does it mean? A is a matrix which is a mirror, and X is being mapped as B. So if you have A, it is you are getting X equals to B. X is B. It could be concave mirror, convex mirror. When it will be a plane mirror, same image you can get. No. When I can get plane mirror? Identity matrix. Excellent. So if you have Ix equals to B, you can get X equals to B. So this A is nothing but a mirror. Maybe the length of the X could be increased, could be decreased based on A. So and also if you operate A to X, something is happening. Sometimes what actually happens, you know the result. We know the mirror, we can get the object. That is my solution. Right? That is the concept. That is the so whatever problem you do in our daily life is nothing but mirror. Like in Gita, we say whatever you do karma, you get result. Karma is the object, result is the image, and the medium where you are doing karma is a mirror. Okay. So same thing here. Here is in mathematics, we are having solution. We are trying to find solution. We are having something like nu equals to F. That's my result, F. So F is nothing but my mirror. So if I say y equals to fx, that means say y equals to say y square equals to 4x. For example. This is my parabola. Okay. If you write y equals to x square, you will get this type of parabola. Okay. What actually happens? If you give the values of x, you get the value of. You put x equals to minus x equal to 0, you get y equal to 0. X equals to minus 1, y equals to 1. Minus 2, minus 3 similar, you can get plus 1. So, Bohr's law of set, if you supply, these are, so what actually happens? My points are here. These are my points. When I apply this function y equals to fx, these points are coming here, and that's my parabola. Okay. For entire set of x, if you apply fx, you will get this parabola. Sometimes you get y equals to x. That means what? That means, so in that case, this is called as, okay, identity, because of course y is here, x is here, and this is the reference at this line y equals to x. And here if you see that, see how this point is distorted. If you look at, this is my, if I am in this line, that means my image is not distorted, y equals to x. Now for this kind of function, you can see that so much of distortion here, only this point is same, this point is same, and equal to different. So in this case, the function of x is of course y equals to x. This is nothing but a plane mirror. But for this case and this case, they are having something like convergent or concave mirror or the convex mirror. So that is the way we see. And what actually happens for, if you see the infinite set of points and you will be getting infinite set of points. So with this infinite set, you can automatically draw the functions. For example, how to draw this line? If you have infinite points, then I don't have to draw the line. These infinite points automatically draw the line. Okay? Y equals to x. Infinite points, if you just put it in the MATLAB, you start from 0, then 0.1. Like that 100 points if you put, or 0.01 for example, up to 1 if you put 100 points, you will see that those points itself will draw the line. You don't draw the line. And that means this continuous function is the result of all these 100 points. And that means that if you have this set of these x, you will get the set of y, which is same, x and y same. This 100 set or maybe 1,000 set will be giving you the straight line. Okay? That shows again functional space is infinite dimension. Infinite number of component of vectors. So functional space can be viewed as infinite dimensional vector space. Functional space can be viewed as infinite dimensional vector space. Okay? I don't know whether you could look at the function in this way under your school level. If you look at the school level, college level, in a different way. Okay, if you look at it and appreciate better, everything is same what we are doing in mathematics. It's not different. Okay? This one is clear of the functional space. So many ways we have looked at how a differential, how a functional space problem can be converted and in fact this entire problem can be converted to a vector space problem. How is that? Entire problem can be expressed as a vector space problem. You are sleeping continuously, you are having some problem, you do one thing, last bench you go and sleep there. Please go, no, you go, sir. Now, sir, please. Okay? Please go, otherwise I cannot continue the class. Last bench, after him you go. Then you cannot nice sleep. Last bench, yeah. After him, that's it. My finger is there. That's it. Okay. You got the nice place. Now you sleep. Fan is also on. No problem. Okay. Thank you. Okay. So now the situation is y equals to x. How can I convert the vector space problem? Vector space problem I want. This is the functional space. Y equals to x. How to express, how to convert the vector space?
Identity matrix 0, 0.01, 0.02.
No. Why all those things? Y bar equals to x. Okay? X you give the values, we get the same value y. How to do for this vector space? I want to convert y equals to x. See, differential operator is very easy. You can do approximate and do it. But this is dangerous. This is a real function. I am asking y equals to x square. How to convert to x equals to b? Differential take. Okay. What is madam saying? There is some approximation. You are saying dy dx equals to 2x. You are saying d2y by dx square equals to 2. Right? Okay, boundary condition. It's very easy. At x equals to 0, y equals to 0. At x equals to 1, if you want, y equals to 1. This is one of the approximations. I hope it will work. Okay? So this is one of the ways. So she wrote she wrote fantastically. So in that case, you can actually convert this thing, this as a vector space problem. You can see that everything is same. Whatever is functional space, any vector space. That's what my point to show that everything is actually same. Okay, so I think you can convert. I think what's your name, madam? What is that? Ramaya. MS, right? You are doing MS? Okay, PhD. Okay. So what you do that? I think this part you can submit on Monday. Whatever I am teaching. Okay, if you understand better, or maybe Vasudha can actually join there to submit, because of whatever lecture I am giving today, it is not there in my notes. Because yesterday I was thinking philosophically how to address, and that's what I'm actually teaching in the class. Okay. So next is so we have actually seen unified approach, vector space versus functional space. So if I give any equation, say for example y equals to x cubed plus 3x squared, say 5. If I want you to ask, if you find out how to have the vector space presentation for this, I hope you can do it. Right? Any complicated function. Complicated function is dangerous if you believe that. But always finite difference can help you. And you can see whatever you are getting from the finite difference. Analytical adjacent. So what I actually ask you that I want you to take complex function like sin x to the power log x, something like that. Apply the technique, get dy by dx for whatever. Okay? Or if you can get dy dx. If you can, in fact, you can actually have dy dx. For example, y equals to x squared. You can take dy dx, no problem. At x equals to 0, y equals to 1. Solve it. First order differential equation. Okay? What is your things? yi plus 1 minus yi by delta x equal to 2x. Okay? And you can, in that case, we can have a matrix. And matrix, you solve it and see whether those discrete points, maybe we are taking 10 points. By solving 10 points, this is your vector space solution. Sorry, these are functional space solution. Functional space. And these are discrete points. These are vector space. I want you to consider some test cases based on your choice. Maybe one can submit 3 or 4 by Monday, it is due. Any complicated function means you get extracted. And I want to see how this comparison is. MATLAB you can plot. MATLAB you can solve the system. If you have made a b, you know that it is a backslash b is equals to x. You can solve. It's a inverse b. You can use MATLAB. But every document, actually I want, maybe Vasudha can do, Nikita can do, or Ramaya can do. So, or somebody else, maybe Amit, if you want, you can pick up 2 problems. Some complicated function, simple function won't have much chance. And see how your approximation, finite vector space and the functional space, how they are actually carried. That's the way your understanding will be. It may differ, if it differs, why it differs. So these are the challenges. Okay. We have seen that vector space, functional space, both are same almost. The same thing, just representing in a different form. Now, the definition, of course, numeric field, we will write vector space. There is nothing called numeric field. So, next thing is the properties of the functional space. First is metric. So, whatever I wrote in the very beginning today, the first day, that part we have to address it. Okay? So, the properties, whatever is valid for the vector space, will it be valid for the functional space? have studied basis vector. It will be basis function. How they are. How many basis functions they are in? These questions will become. We discussed in vector space. Eigenvectors are the best basis vectors. Can we have something called eigenfunction? Are they the best basis functions? How to construct eigenfunction? Next, that will be our test. We have done adjoint theorem. Will that be valid here? Adjoint theorem. So this is the way. So what I am going to discuss next, whatever we have studied in vector space, the same things are, because we are not declaring vector space, functional space, they are like brothers. Cousin brother, own brother, I don't know. They are the same, maybe twins, we don't know. Sometimes they act as twin brother, sometimes they may not. Okay? So that means same thing. Whether one brother is doing something, another brother is different. No, same thing. Some difference will be there. I can tell you that functional space is more mature, brother. It can handle so much complications. Vector space is like, very simple guy. It cannot handle much complicated things. So I will discuss all those things with you. So whatever I am teaching this notes, Vasudha or Tanmay can actually do it because it will be helpful for me, because nothing is there in my notes. Because all those things, whatever I taught yesterday, that I taught so far. So properties of functional space. Properties of functional space. First is metric. Number one is metric. What is metric? Distance between two vectors. Excellent. So I have two functions, fx and gx. Now, any function you can imagine as an infinite dimensional vector. So now it is easy for you to visualize. This is a vector. Dimension is infinite dimension. So you can say, I will write it f bar and g bar, infinite dimension vector. I will write, but for your convenience I will say. How to define distance between these two infinite dimensional vectors? How to define the distance between two infinite dimensional vectors? The distance between two vectors, what was x bar and y bar? How to write dx bar y bar, which is summation xi minus yi whole square root, right? Summation. Similarly, what we can do, we can write this as d fx dx. If you think about it, I am just pursuing summation I equals to 1 to infinity fi minus gi whole square, infinite dimensional. I equals to 1 to infinity. Now I will have the concept, if I equals to 1 to infinity, is this summation can be replaced? That's what my question is. So let's do that. A function y equals to fx. What I am doing? I am taking infinite subscript. Okay? So it is having y1, y2, it is like y infinity. Okay? And it is nothing but f1, f2 and f infinity. So actually having summation fi, if you add all the speed, if you leave summation fi, I equals to 1 to infinity. Right? What does that mean in calculus? Integral f dx. This means integral f dx. If the limit is from 0 to 1, you write 0 to 1. So summation is replaced by integral for the infinite dimension. So, what will be the dfx dx? Integral a to b, not fi, fx. Now fi will not be there. It's a vector represent minus gx. Then whole square. I can tell you that your textbook or none of the books have this kind of explanation. Whatever I am teaching today, nothing is there in any of the books, including this one. How the definition of metric is coming in the functional space. Is the conduct clear? Okay. Conduct clear? Okay. So next, I think we can easily define norm. Next, we can easily define norm. Okay. How to define norm in vector space? Say U bar. Norm of U bar we call 2 norm summation ui square whole to the power half I equals to 1 to 2. In functional space, norm of fx we try to define I equals to 1 to infinity a for 5 a square whole to the power half, but the real definition is whole to the power half is there, and then who will tell me the answer? Integral a to b f of x square. You are not saying the square. F of x square dx. See how easy? So this is the norm of the functional space. That is the length. So basically, this is nothing but the length of the function. Length of the function. Now you can see the in function can be expressed as a infinite dimensional vector space. So function, if I say norm of the function, it is nothing but the length of the function. Because any function, a particular range, if I say function, when you define a function, we always define a range. Okay, a to b. Range is there. Otherwise, function definition is not valid. Because function may be discontinuous, you don't know. So function has to be given the range, a to b or 0 to 1. In that particular range, function can be expressed in infinite dimensional vector space and norm of functions, the length of the function. So far we are seeing whatever we have learned in vector space, all properties are actually valid here. Next is inner product. Next is inner product. Next is inner product. Inner product, vector space, what we did? Inner product UV, which is summation I equals to 1 to n ui di bar. Inner product fx gx should be equals to, directly should write, integral a to b, not ui, fx boss, fx g of x bar. Excellent. So everything is valid, whatever we have learned in vector space. Okay. So next comes the basis. Next comes the linear independence and basis. So let's talk about what are the criteria for the linear independence and the basis. In vector space, if I say u1, u2, un form basis, if a vector u can be expressed as a linear combination of basis vectors. Okay? And for this is, of course, linear independence. Basis means summation alpha I to I bar equals 0, and in that case alpha I has to be 0 for all I. Right? Alpha I has to be 0 for all I. Correct? Functional space. This part is clear for all of us. For functional space. Phi 1, phi 2, phi n form basis. Of course, they are x, x, x. Such that you tell me the answer, you do the answer. It is there in the board. From the basis. This is linear independence. This is the basis. Summation. In what integral? Don't do like this. Or you are actually trying to. That is the problem with you guys. You are just trying to convert everything into integral. What is the basis? I am just telling you, you are actually apply your brain, you know the answer. This is the vector. Triangle rule. Okay? This is my u vector. This is my v vector. And this is my w vector. So w vector is u vector plus v vector. Okay? Now, if w is infinite dimension, u is infinite dimension and v is infinite dimension, I can write wx equals to ux plus vx. Where the integral coming, I don't know. That's what your problem is. You directly, you see, this is the way actually you prepare the gate exam and you have the bullets. You somehow crack the answer and put the bullet. And if you do that, you won't apply the brain. And that's the problem here. Okay? So, with the integral will come, of course integral will not come. Ws integral will come. That means it's a very dangerous thing. You are saying, how do they integral? You are saying, if I have so many basis functions, you will say all infinite integral are not a dangerous function. I can't even think about it. And it doesn't make any sense. It makes sense. This is correct, right? This we know. This is just simple extension. Any vector can be expressed as linear combination of basis vectors. Okay? And if there is a unit vector, say E1 and E2, you can write W bar as alpha 1 E1 bar, alpha 2 E2 bar, alpha 1 alpha 2 are documents. For the vector space. Functional space, we can, if phi 1, in that case, we can write E1x and E2x. Unit infinite dimensional vector. Okay? Another basis, unit infinite dimensional vector. We can write W equals to alpha 1 plus alpha 2, alpha 1 E1x plus alpha 2 E2x. Same thing, it's a very easy concept. I don't know why you got the integral. Integral is very complex. I never thought about it. What will have an integral? Dangerous. Right? Whatever we visualize in the physics, it is coming out here exactly. Right? Is that correct? Yes. Okay. So, what will happen? What is my this thing? As I said, it's written in the board. What is the condition for the basis? Sigma summation alpha I equals to 0. And there is a problem. There is a problem here. Where is the problem? The problem is, now we see something extra is required for functional space. Up to this, vector space is okay. But functional space, if you write, there is a problem. I will explain the problem. In vector space, your basis was simple basis 0, 1, 0, 0, 0, 1. How to get alpha number and alpha 3? You equate plus alpha 2, 0, 1, 0 plus alpha 3, 0, 0, 1 equals to 0. You write 1, 0, 0, 0, 1, 0, 0, 0, 1, alpha 1, alpha 2, alpha 3 equals to 0. And of course we have seen that it's a plane mirror. Now we can see the plane mirror, and because of plane mirror, alpha has to be 0. What actually we found? This leads three algebraic equations. We have three unknowns, alpha 1, alpha 2, alpha 3. Three unknowns, three algebraic equations, determinant is non-singular, so you get trivial solution. How many equations you have? Infinite equations. See the problem with you don't apply the brain. It is not great exam coaching center. It is an application of brain center. Okay. So, alpha 1, I will tell you how the basis functions look like. So far you don't have any idea. So the next question is to attack this problem. Next question is, how do the basis functions look? How the basis functions look? Basis vectors, simple basis vectors we have seen. These are the simple basis vectors. What you can say, sir, this equation is, what is the equation of this one? Function of yz equal to 0. Function of xz equal to 0. And function of xy equals to 0. Very complicated because I am working only in one dimension. How can you get x, y, z? So forget it from writing from here. How the basis functions look like? For the case y equals to function of x, only one variable. Multiple variable don't talk about, dangerous. We talk multiple variable in my final element course, not here. Here only function of x is allowed. Only single variable for this course, very easy course. We don't have any complications in life. This is my domain. This is my domain. Because you can say that, okay, this is for function space, why you need 2? You are saying infinite dimensional because you are collecting infinite points and putting into one block paper. Okay? And here, on individual points along the axis. That's the difference. In individual points along the axis, and all individual points you are collecting together and putting in one block. That's why you could see infinite dimensional vector space in a 2D plot. And finite dimensional vector space require 3D, 4D, 5D plot. Because each point represents another direction, coordinate axis. Right? Then, next. What in this plane? So now we have to think a different way. Okay? So one thing can be, one function I can draw. This could be one of the function, basis function. Or this could be another basis function. Okay? Or this could be another basis function. So many structures are there. So I am saying that you can verify the basis functions. At the simple basis function one can think about. Okay? These are basis functions. So the first time I will put this in 1. X square, x to the power. Okay? First one is 1. Whatever the value of x, you are getting 1. Second one is x. Y equals to x. Next one is x square. So what I am doing that, see, what's the rationale behind this? This is not varying. This is linearly varying. This is quadratically varying. And you can see if it is cubic, then there is a curvature change. So if you have a complicated function, the complicated function has to be built from the constant function, linearly varying function, then you are changing curvature. For cubic,